Hello, grade 12s. Let's move on to our next lesson, which is going to be about inclined planes. So in class, we did our forces in two-dimension and multiple mass systems notes, and now we are moving on to the next one. So hopefully you have finished the practice problems on that, and we can learn about some new concepts here. So generally, so far, when we've been solving problems involving vectors, we use components so that all the vectors are going to be in either the x or the y direction. We need them to be in the same direction so that we can add them up easily. This doesn't change when working with inclined planes necessarily. We still want to have an x and a y direction. So we still need to calculate the components, but we just don't use the typical x and y directions that we would in previous problems. The reason we do this is that if we tried to do everything on an X and Y, but we had things on an incline, we'd have to do a bunch more components calculations. So this way we can avoid some of those components calculations and we can just boil it down to one components problem or one component's necessary component step. And then the rest of the question should just be in our X's and Y's, which is nice. So it doesn't really make total sense until we get started. So let's just start and it will make sense. 100 kilogram mass is on a frictionless incline of 25 degrees. To keep it from accelerating down the slope at too great a rate, the person exerts a force of 400 newtons directed up the incline. So we've got something sliding down an incline, and then we've got somebody acting opposite that direction of motion that it wants to do. It wants to slide down that incline. So we've got two questions here. The first question is calculating the net force on the mass. The second question is calculating the acceleration. So let's start off by just drawing what's going on. We have a slope, something like that our object is on. And that slope, or that incline, is 25 degrees. Almost drew a 3 there. 25 degrees. And then let's draw the mass that we have on there, the 100 kilogram mass. There it is. We can even put a little 100 kg in there if we want. And now what else has the question told us? It says to keep it from accelerating downwards at too great a rate. So acceleration is going to be down this way. So we could even include that. Acceleration is down this way, which is important to know because we're only ever concerned with the forces that are acting in the same direction as the acceleration, right? So our net force that we're going to be worried about is going to be in this same direction as the acceleration. Now, in order to oppose that direction of motion, I'll outline this here. We've got somebody exerting 400 newtons of force in the opposite direction. 400 newtons of force, and we'll call it FA. It's the applied force acting on the object. Now, I want you to just take a second here to think about what other forces are acting on this object. We're not going to concern ourselves with friction, right? Because it says a frictionless surface, so that's important to note. We don't have to worry about friction. We do have something that's making this object want to slide down here, though. That's gravity, right? But gravity, we're used to acting straight downwards when we do questions like this, right? But gravity in this case always acts towards the center of the earth. So gravity is actually going to act like that. That's going to be Fg. And then normal force always is the force exerted by a surface that has something pressing down on it, right? So in this case, the force exerted by the surface is going to be perpendicular to that surface. So our normal force will look like that. So now we've got our first scenario where we don't have Fg and Fn acting equal and opposite. So this is why we need to do this technique that I was mentioning here that I brought up briefly, is that we need to think about not our typical X and Y directions. We're actually going to do this. We're going to imagine for a bit here that this incline doesn't exist in a way, and we're only looking at a problem like this. If this were the case, then this would be my y, and this would be my x, and this would be positive, and these would be negative. Okay? But that is not in fact the case. So this is this different x direction that we were talking about. We're just going to look at the x and y in perspective to, or in relation to, the slope that the object is sitting on, the inclined surface. So what does that mean? What does that mean for what this FG is going to be? Well, this is the one scenario here where I now need to calculate components, because I will have a quote unquote y component of my FG here, and I will have a x component of my FG here. So you have something called FGX and FGY. And this angle right here is actually 25. Okay, just using basic trig principles, we can see that this is also going to be 25, just like this is. So that's nice. That's telling us a lot of information then, because right, we can actually now, if we know that that's 25, and I know what FG is. FG, remember, is always mass times gravitational acceleration. Well then, FGY is just equal to FG, is it opposite or is it adjacent? It's going to be FG cos of 25 degrees, which I can replace with MG cos of 25 degrees. And FGX is FG sine of 25 degrees, or mg sine of 25 degrees. And we know the mass and we know g, so we can technically find both of these things. Now, before we get too carried away and we spend too much time on this, it's actually not quite necessary to use both of them. We're only concerned with one of them. We're only concerned with one of them. Which one would it be? Well, our problem here, the question is asking, what is the net force? The net force I mentioned is going to be in that x direction, because that's the direction that the acceleration is acting in, right? So our problem, what we're trying to find here, is what is F net x? So F net x, when in doubt, okay, when in doubt, we just need to look at the fact that it is going to be a combination of the components acting on that object. And we don't know what acceleration is, but that's okay, because we're just trying to find net force. And to find net force, we just need to add up all of the forces acting on that object. We can find acceleration right after, right? So this is our scenario where we'll be F net x equals ma. We'll get there, but we need to find F net first. And F net is that applied force acting up the slope and the x component of the gravitational force, which is wanting to pull that object down the slope. So those are our two forces in the x direction that are contributing to the size, or to the net force that we have acting on that object. So FA is positive, right? We'll now go F net. We'll get rid of our vector arrows. FA is going to be positive 400 plus mg sine 25. M is 100. G is down, right? G is going to be down. So negative 9.8 sine of 25 degrees. And if I do that, I should get 400 minus 414.166. If you plug this all into your calculator, you get negative 100 or 414. So our final answer is going to be negative 14.2 newtons. And if I'm actually concerning myself with the proper amount of sig figs, It's actually an unfortunate setup here because the question actually has a minimum amount of 1 sig fig. So we'd have to actually round this to 10. So negative 10. Or instead of putting negative, we'll just say 10 newtons down the slope. And the reason for that 10 is just, again, because we're only using 1 sig fig in the question. So there you have it. There's our net force in the x direction. What about trying to find acceleration now? Well, actually, you know what? We've done a lot of the work to set it up here. We've got m equals 100 kilograms. I would highly suggest in this scenario not using 10, but using 14.166. So let's write that down so we don't get confused. F net x is 14.166 newtons. We'll say down the slope. And we're trying to find acceleration. So A, if we rearrange our formulas like we're getting so good at doing, we get A equals F net x divided by m. And plugging in our values for that, we get negative 14.166 if I'm just going to replace my vectors with my scalars now, and 100. And so our answer should look something like negative 0.1417 or 166. So we'll call it acceleration equals 0.14 meters per second squared. And then again, it's down the slope. And we'll have to just do our 1 sig fig because I don't have room to rewrite it in using the scientific method, scientific notation. So anyways, I just had somebody walk into the room. Yeah, apologies, they're coming back. So anyways, that is our answer. We've got an acceleration downwards still, but we're diminishing that acceleration by applying that upwards force to it. So similar setup, we just now have to think about everything kind of on a tilted axis. Okay, so that brings us to example number 2. And in this case, now we'll have a similar setup, a similar question, but we have a friction force acting on the object as well. So let's take a look at how that changes things. A 20 kilogram mass is on an incline of 15 degrees. So let's draw our, this marker is running out of ink. 15 degrees. We've got our object, 20 kgs. Okay, and then let's draw all of the forces acting on that object. So we have a force of 150 newtons is applied to the mass directed up the incline. That's FA. 80 newtons of friction is acting on the mass. That would oppose, the mass is accelerating up the incline. So again, I can do this. Acceleration is going up the incline. So that means that friction force always opposes motion. I made that way too big. I'll use my whiteout. So friction force always opposes the motion. So we know that that's going to be acting down the incline. Okay, so we'll just write out our little FF here. And then what else do we have acting on it? We have gravity that's also opposing the motion in this case, acting down the incline, down towards the center of the planet. And then we've got normal force, which is acting perpendicular to the surface that it's on, always. So then our next step would be to break down Fg into its x and y components. We've got Fgy and Fgx. And then we are concerned with the acceleration, which is up the incline. So we know that our forces that are going to be of concern for us are going to be applied force, frictional force, and gravitational force, the x component only. So our next step will be to write out our F net x equals ma. So we'll set up our formula here. We know that we're going to be using F net in that x direction. X again, let's do this. Let's not get moving too quickly here. We got x and y, and we'll make these positives and these the negatives. And we know that we're trying to find what acceleration is equal to. So let's actually take 1 second here to just write down what all of our stuff is equal to here. Fa is equal to 150 newtons to the right or up. You know what? I should be more specific with that. It is to the right, technically. To the right on our slope. And then we've got Ff, which is the friction force, which is 80 newtons in the opposite direction. And then we'll have Fgx. That's the other one right here, right? We're looking at all the stuff that's in this direction, up and down the slope. Because there's no acceleration happening up off the slope or down into the slope, right? So Fn and Fgy are just going to cancel each other out perfectly. So Fgx is going to be mg, we could just get used to writing it like this, mg sine of 15 degrees. Where did that 15 come from? Well, right here. It's the same as that angle right there. So mg 15, and mg comes from Fg, right? So, let's write out our formula here. So F net x equals ma, and let's add up all of our forces in the x direction. So we've got applied force up, friction force opposing it, gravitational force x component only equals ma, and let's divide by m on both sides. Divide by m on both sides will give us a. I'm going to get rid of my vector arrows here. I'm going to start plugging in my values. So I should get FA, which is 150, but it's positive because it's to the right, plus FF, but it's negative 80 because it's to the left, plus MG, so M is 20, G is negative 9.8, sine of 15 degrees. And then I said I was dividing by m on both sides, so my m is 20. Do all of this up on the top here first, and then divide by 20, okay? Let's not get our order of operations here confused because we've got so many things happening. I plug all of this in my calculator, 150 minus 80 minus 20 times 9.8 times sine 15, divide by 20. On the top, I should get something that looks like 19.2715 divided by 20. That's what you should get. And if you plug that into your calculators, you should get something like 0.96 meters per second squared, and it's positive. So our final answer, A, is, let's take a quick look at our sig figs. It looks like we've got 1 sig fig again, so I'll round that up to 1 meter per second squared up incline, we'll call it. So there you have it, ladies and gentlemen. An introduction to inclined planes. I hope that made some sense and you were able to follow along. Please email me if you have any questions, and if not, you can do the associated practice problems with this before the next lesson.